Love them or hate them, we interact with speed limits every day. Because they're so present in our day-to-day lives, it is important to understand exactly how speed limits are designed and their significance. So, how are speed limits set?
They may seem unfair to those drivers who see speed limits as minimums, but speed limits are actually designed with these drivers in mind. Traffic engineers determine speed limits by conducting a study of the traffic on a given road. They use a sample size of vehicles deemed sufficient for the given road and take the speed of each vehicle on the road. The traffic engineer then calculates the distribution and standard deviation of the vehicles on the road and finds the 85th percentile of speeds, which the speed limit will then be set as.
If you're driving uphill on a steep slope, you may feel compelled to hit the gas, but a downhill driver may want to slow down to feel in control of the vehicle. So, why are uphill and downhill speed limits set the same? Uphill and downhill speed limits are the same because the difference between uphill and downhill stopping distance is quite small. For example, for the stretch of road we analyzed on Highway 20, the difference between uphill and downhill stopping distances is approximately 5 meters even on a grade of 3.853, which is quite steep for a highway. The uphill stopping distance was estimated to be 103 meters, and the downhill stopping distance 108 meters. This insignificant difference allows uphill and downhill speed limits to be the same. How did we figure that out? Allow us to explain.
We began by picking a stretch of road on Highway 20 near Mountain Home, Idaho. We made a note of the distance along the road, which functioned as our horizontal length, and made note of the elevation at either end of the stretch. We then wrote down these values and used them in our next equation. In order to calculate the grade of the stretch of the highway, we used the equation rise over run. Rise was equal to the change in elevation at either end of the stretch of the road, and the horizontal distance, the run, was equal to the horizontal length we previously measured. Once we plugged in those values, we got the answer, which was our grade.
Now that we have our grade, in order to calculate stopping distance, we use the AASHTO formula for stopping distance. This equation states that the stopping distance is equivalent to 0.278 multiplied by reaction time and then velocity, plus velocity squared over 254 times the sum of friction plus the grade of the road. This grade is positive on an uphill and negative on a downhill road.
We then use the AASHTO formula to calculate the stopping distance uphill on our stretch of highway. We converted our 65 mph velocity to 104.61 km per hour, and set the reaction time to equal to 1.5 seconds since this is our average driver. We then use a frictional coefficient of 0.7 since this road is dry for most of the year, and calculate a final braking distance going uphill of 102.641 meters. We then use the AASHTO formula to calculate the stopping distance downhill. We followed the same procedure and kept the same measurements, except this time we subtracted the grade of the road, seeing as we were traveling downhill. We calculated a final stopping distance of 107.926 meters. We then used the third kinematic equation in order to find the acceleration for our car traveling uphill. The equation is velocity squared equals velocity initial squared plus 2 times acceleration times the distance traveled. We plug in our velocity of 29 meters per second, which is equal to 65 miles per hour, a braking distance of 102.641 meters, and a final velocity of 0 meters per second. We then calculate the acceleration to be negative 4.114 meters per second squared. For the downhill acceleration, we use the same equation and measurements, except we change our distance traveled to the downhill braking distance, which is 107.926 meters. We then solve for an acceleration of negative 3.912 meters per second squared traveling downhill.
In order to calculate the time it would take for a car to stop traveling uphill, we use the first kinematic equation. Velocity equals initial velocity plus acceleration times time. Using the initial velocity of 29 meters per second and uphill acceleration of negative 4.114 meters per second squared, we found the stopping time to be 7.021 seconds. In order to calculate the downhill stopping time, we used the same procedure but changed the acceleration measurements to negative 3.912 meters per second to reflect the lesser acceleration downhill. This produces a stopping time of 7.495 seconds when going downhill. We compiled a table listing our results for cars traveling either uphill or downhill. Based on the table, we found a difference in stopping distance just over 5 meters, a difference in acceleration of about 0.2 meters per second squared, and a difference in stopping time of just under half a second. We also made note of how we assumed dry conditions for a frictional coefficient of 0.7 and an average driver's reaction time of 1.5 seconds.
What is important to recognize is that driving uphill on a steep grade, your car can accelerate and consequently decelerate faster, which makes it easier to stop in a shorter distance and in less time. On a road of this grade going uphill at 65 miles per hour, you can come to a stop in just under 103 meters, and driving downhill at the same speed, you can come to a stop in 108 meters. Even though the difference in stopping distances may seem small, It is key to understand that while driving downhill, you need to be more cautious about your speed in order to maintain adequate control of your car on the road. This is especially true when driving conditions are subpar. If a driver is older, tired, or distracted, if the road is slick and properly maintained or steep, then the speed limit should be treated as a maximum, because in these conditions reaction time is slower, friction between the tires and the road is decreased, and stopping distance is longer. So each time you drive, keep these factors in mind and adjust your speed accordingly.
Congratulations! 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 Congratulations!
Congratulations.
Congratulations!
Congratulations.
Congratulations! Congratulations!
Congratulations.
Congratulations!
Congratulations!
Congratulations!